Alaikum. Let's start lecture number 28, and we will continue chapter 5. We will cover last topic for chapter 5, that is design of prismatic beams for bending. Now, previously we studied how to draw shear force at bending moment diagram, and using the equilibrium condition, that is sum of forces is equal to 0 and sum of moment is equal to 0, taking sections, and we find the force and moment, shear force and moment in internal section. Then we discuss about relation among load, shear, and bending moment, and that is known as graphical method. Now, for the design of prismatic beam, we need maximum bending moment that we can find through this bending moment diagram, and by applying the formula, flexible formula, we can design the beam. Let's see. So the largest normal stress is found at the surface where the maximum bending moment occurs, and that maximum internal bending moment we can find using by the shear force and bending moment diagram. Okay, now the maximum bending stress, normal stress, we can find mx c over I or mx by s, where s is section modulus, and that s is equal to simply s is equal to I by c. So this is known as section modulus. Okay, now for safe design requires that maximum normal stress be less than the allowable stress. Means depending on the allowable stress is depending on the material used, and this criteria lead to determine the minimum acceptable section modulus. Means we know the loading, we know the material, so what will be the dimension we can find using this relationship. It will give us the section modulus, and that's using the section modulus we can have we can design a cross section of the beam. So among beam section choice which have acceptable section modulus, the one which is the smallest weight per unit length or cross sectional area will be the least expensive and the best choice. Means we have some standard beams as well, so we will select that standard beam which have acceptable range of S minimum and which have smallest cross section. Okay, so the cross section should be small. Why? Because the smaller the cross section, for the same length of the beam, the weight will be less and it will be less expensive. So, or in some cases you have to design or decide what will be the cross section of the beam, and we will see. Okay, now let's see an example sample problem, that sample problem 5.8 from the book. So that sample problem is the statement is a simply supported steel beam is to carry a distributed load and a concentrated load shown. So we have a simply supported beam AD with a distributed load of 20 kilonewton. So this should be 20 kilonewton meter. So this is, it should be written as, let me write over here, 20 kilonewton per meter. We have 50 kilonewton load acting downward direction over here, and we have a support at A and D. It's a simply supported beam with a distributed load and concentrated load. Okay. Knowing that allowable normal stress for the grade of steel to be used is 160 megapascal, select the wide flange shape that should be used. Means we have to find the shape of the beam, that is W shape beam, and that the standard size are given in Annex C of textbook. Okay, from Annex C we have to select W shape beam for the grade steel We will grade of steel with allowable normal stresses 160 megapascal. Okay. Now, what we will do? We will first consider beam as a free body, taking entire beam as a free body and determine reaction A and D. Then we will develop shear and bending moment diagram and to find the maximum bending moment. Okay. And using that maximum bonding moment, we will apply the Flexible formula to find the section modulus, and from the section modulus, the minimum acceptable beam section modulus, choose the best section which meets this criteria. Which criteria? That it must have uh, minimal cross-sectional area. Okay. Now first we will find reaction at D and A. So sum of moment at D should be equal to A should be equal to 0. So we can find the value of D, and sum of moment, sum of forces acting downward direction is equal to 0. So with we know the value of D, putting the value we can find AY. Okay. Now shear force diagram. So shear force diagram between VA is 52 kilonewton. VAB minus VA, that is area under the load curve, minus, so area under the load curve is 60 kilonewton. So that will become minus 60 kilonewton, and VA is 50 kilonewton. So let me write over here, let me write, so VB, so we can write VB is equal to minus area under the load curve, that is 60 kilonewton, and plus 52 kilonewton, that is the value of VA. So VB is minus 8 kilonewton, and the variation will be linear, and it will be minus 52, and at D it will be minus 8 kilonewton, and it will be 0 at some location that we will see. Okay. Now maximum bending moment occur where V is equal to 0. So this V we can find graphically. So that graphically we can find, or we know this triangle. So this value, we know this height, we know this height, and we can find this value. Okay. By taking this total is known 3. So from E to B that will become 3 minus x, and this is x. So the value, the location of E we can find is simply a similar triangle, that 52 by x should be equal to 8 by 3 minus x, and with following this we can find the value of x, and it will be the maximum bending moment where the shear force will be 0. It will be, and it will be area under this shear force curve. So this is a right angle triangle. So the area is simply 1 by 2, 52 kilonewton multiplied by 2.6. So this will give us the value of 67.6 kilonewton, and kilonewton meter, this should be meter. So this is a maximum shear bending moment acting on the beam, and we can use this bending moment. So section modulus will be max by sigma allowable. So 67.6 kilonewton meter divided by 160 megapascal, that is allowable stress. So we put the value. So S minimum, the minimum section modulus acceptable is for 422.5 10 to the power minus 6 meter cube, or for 222.5 10 to the power 3 millimeter cube. Now what we will do, we will look at the Annex C. W-shaped beam, and the data is available in NXC, and we will find that these are the beams that listed on this table. So these beams has a section modulus near to this 422. So if you look at that 637 millimeter cube, 10 to power 3 meters, so W 410 by 38, and we have W 360 by 32.9, we have 310 by um, 310 by 38, and so on. So why we choose the best one? So if I look at the area of those beams, so if I look at the area, the first one is 410 by 38.8. So the area for that is 4,950, and that is in millimeter square. Now W360 by 360 by 32.9. So the area for this beam is 4190. For 310 by 38.7, the cross sectional area is 4940. And for 250 by 44.8, the cross sectional area is 5700. And for the last beam, 200 by 46.1, the cross sectional area is 5880. Now we will select the beam which has a minimal cross section because it will be least expensive, and it also serving our purpose as well, because the section modulus is within the acceptable range of 422.5 10 to power 3 meter cube. So choose the best standard section which meets this criteria, so that is W360 by 32.9. So this beam, cross section beam, is optimal uh, for the loading shown previously. Now let's see another problem from the book. We will solve the problem step by step. So let's see problem 5.87. Determine the largest permissible value of P for the beam and the loading shown, knowing that the allowable normal stress is plus 8 in KSI in tension and minus 18 KSI in compression. So beam A, B, C, D, E is shown. It's an overhanging beam. So it has a support at B and D. So load P is applied at A, C, and E, and the cross section is given. So we have to find the permissible load P, and we have a condition that normal stress in tension is 8 KSI allowable and minus 18 KSI in compression allowable. So we have to find the maximum value of bending moment, but we have to consider the cross section as well. So for that, we have to draw bending moment diagram. We have to find shape force. We will draw shape force and bending moment diagram for this problem. And first we have to find what is the reaction at B and D. For that, we draw free body diagram for the whole beam with the force P acting at A, C, and E. And now if I take moment at moment at B is equal to 0, I can find the value of D, and if I take moment at D is equal to 0, so I can find the value of B, and these values will be simply 1.5 times P. Okay, now we need the cross-sectional property as well. We have to find the stresses, and so first we have to find the location of centroid. So dividing into two sections, 1 and 2, taking a reference at this bottom, and we have to find the location of centroid. So we have two sections, 1 and 2. So A naught area of each section, Y naught, that is distance from the reference bottom to the centroid of the section 1 and 2, and then A naught, Y naught. We multiply these two values, and Y bar is we're putting the value 17.5 plus 3.5 divided by 5 plus 7. So it become 1.75 inches from reference, means from bottom. So the distance is, sorry, 1.75, not 25, it will be 1.75. Okay, and we have to calculate moment of inertia. So I will be equal to I1 plus I2, and we have to apply parallel access theorem, 1 by 12 BH cube for first one, B H cube, B is 1, H is 5, area into D square, D is 1.75 square. That is distance from the centroid of this composite section to the centroid of the section number 1. This is my T1, and similarly this will be my D2. And I2 will be 1 by 12 BH cube plus area into D2 square, and D2 is 1.25 square. So the total value of I is 37.25 inch form. So now let's draw a shear force and bending moment diagram for this problem. Okay, first we are taking section, and we took a section, and we are considering for segment AB. Considering segment AB, so I can write shear force acting downward will be positive, since we are taking section from A to B. We are going from right to left like this. So V1 plus P is equal to 0, and V1 is equal to minus P, and this is valid for section AB. There is no distributed load between section AB, so this V1 is constant between A and B. And similarly, moment, if I want to write M1, so M1 I can write that will be equal to, sorry, M1 plus P into X is equal to 0, and M1 will be simply equal to minus Px. Now, at A, so X will be 0, so MA will be equal to 0. Now at B, this leads us to X is equal to 10 inches. So if I put this in 10 inches, so MB will be equal to minus 10 times P. So it will be 0 at A, and it will be 10P at the value at B. Now let's see this. These are the moment and shear force on segment AB. Now considering segment BC, uh, so first we have to find shear force. So shear force, we can write V2 plus P minus, this is B, minus B is equal to 0, and we know the value of B, that is 1.5 times P minus P. So V2 is simply 0.5 1.5 times p, and it will be constant between this segment B and C. So it will be constant along this segment. Now, moment, let me write M2, and we have plus P times X minus B into X minus 10 and is equal to 0. And this is only valid from B to C. Or M2, I can write simply P, changing the value of B, that is 1.5 times P. So I can write, let me write over here. So this will be 1.5 times P into X minus 10 plus Px. Now, at X is equal to 10, that will become MB, and we already calculated what is MB. So if I put X is equal to 10 inch, so it will become MB, and we already calculated that is minus 10 times P. Now, if I put X is equal to C, that is what, 70 inch, because if you look uh, the figure, so from A to B that is 10 inch, from B to C that is 16, so total will become 70 inch. So if you put the value of and that is at C, so MC will be equal to 1.5 times P, 70 minus 10 minus, sorry, this should be minus, not plus. So let me correct this one. So this should be minus. Okay, and minus P into 70, and by simplifying it, so MC will be equal to 20 times P, and it will be linear because it will start from minus 10P from B, and it will be 20P at C. Okay, now let's calculate on other segment as well. So considering CD, again taking section from left to right from here, so I can write V3 plus P, this one, this P, plus P at A, and minus B is equal to 0. And V3 will be simply putting the value of B in this equation, so it will be simply minus 0.5 P. And this will be a constant throughout CD. Now, considering moment, now if I want to write M3, so it will be plus P into X minus 70, that is at C, this one. So let me change the color. Uh, let me write again with different color, M3. So M3 plus P into X minus 70 plus P into X minus B into X minus 10, and this will be equal to 0. Or M3 I can write 1.5 times P into x minus 10 minus Px minus 70 minus Px. Now at C we have x is equal to 70 inch. So if you put the value, it will be simply coming back to the MC, and we already calculated the value of MC, that was 20 times P. Now, if you put at D, so this will become x is equal to 70 plus 60. So that is 130 inch. So if you put this x is equal to 130 in this expression, so MD will be simply, the value of MD will be simply minus 10 times P. Okay. Now, now the variation is linear. MD is minus 10P, and we have, so from C to D there is a variation from 20P to minus 10P. The moment will change, and the change will be linear because shear force is constant between C and D. Now we consider the last segment DE. So let me write the expression for the shear force. V4 acting upward will be positive, minus P. The shear force acting, so the force is acting downward will be positive. So V4 will be simply is equal to P, and this is valid for DE segment. So we are calculating for here. And at E, that is free end, so moment will be equal to 0. So now we have the value of moment and shear force on different segments, and we can draw shear force and bending moment diagram accordingly. Okay. Now, if you look at the shear force, so shear force from A to B, we know that is V1 is minus P, B to C we calculated V2, that is 0.5 times P, C to D we calculated V3, that is minus 0.5 times P, and from D to E, V4 was P. And these will be constant between AB, BC, CD, and DE. So if I want to plot, so let me put marking over here. So obviously it is not up to the scale. So this is my B, then C, then D, and E. And it's not up to the scale. From B to A to B is starting point. So the force, shear force's value is P. Now from B, at B, it will shift from minus P to plus 0.5 times P. So here it is 0.5 times P, and it will be constant till C, and at C it will now reduce to minus 0.5 times P, and it will be constant from C to D, and then from D to E it will be positive P. So this is basically shear force diagram. And now for the bending moment diagram, we already calculated the moment at different location, and we know the variation between the shear bending moment as well. So B, C, D, and we have E. Again, not up to the scale. From A to B, now from A it to 0, and from B A to Z, so it will be minus 10p. Now from B to C, it will be, so let me draw again this line. From B to C, it will be plus 20p. So that will be plus 20p. And from B to D again, it will become from 20, it will be minus 10p. And it will be obviously 0 at E. Now, we have maximum bending moment of 20p, and we have also minus 10p, but we don't but we don't know what will be the maximum stresses because of the cross section. Now, if you look at the cross section, okay, again this is the shear force and bending moment diagram clearly. Now, if you look at the bending moment, now if you consider the beam, so that beam is bending from A to B, it will bend something like this, from B to C like this, and then D to E. Now, uh, let me clear. So the beam bending, again this is an exaggerated one, something like this. Okay. Now, if you look at B point, okay, so this at B, the top is under tension and the bottom is under compression. But if you look at C, so top will be under compression and bottom will be under tension, and the distance from the centroid of the section and Y top and bottom is not same. So that's why we have to consider uh, these bending moment, and we have to find the value of P accordingly, and we select the smallest one. Okay. Now, if we consider minus 10p moment, so that is at moment at B and D, so that is moment at B and D, so which is equal to minus 10p. Now, if I put that, and we know that sigma is my over I. We already calculated the value of I, and the value of I was 37.25 inch for. Now, if we consider that MB or M is equal to MB minus 10P, so top will be under tension. Top will be under tension, and the stress will be allowable stress. We know that 8 KSI is equal to minus 10 times P, that is bending moment, and we have value. So Y top is 4.25 and divided by 37.25. And this gives us the allowable P of 7.01 KSI. Now, bottom will be under compression, So we can write the allowable compressive stress is minus 18. So let me 18 KSI. So the value is again 10p. Let me clearly written that. So 10p. Now distance is 1.75 divided by 37.25, and the value of p will become 38.3 KSI. Now, if we consider moment at C, that is equal to 20p. Now, if we look at that, bottom will be under tension and top will be under compression at C. So, at C, the top will be under tension and the allowable shearing stress is 8 KSI, 20p moment. Now, distance for the top is top will be under compression, bottom will be under tension. So let me top will be under compression, and this will become 18 psi minus 20. So, and putting the value of top 4.25 divided by I 37.25, and this leads us to value of P is equal to 7.89 ksi, and bottom will be under tension in this case. So we can write 88 ksi into 20p 1.75 divided by 37.25. In this case, the p is 8.51 ksi. ksi. Now, we will select the allowable. P allowable will be the smallest between them, so that is 7.01 ksi. Now, if you look at that, the moment was not maximum. So 20p is the maximum moment, but due to cross section, due to the cross section orientation of the section, so the maximum stresses are at B and D, and that is in tension. So you have to be careful. If it's a symmetric cross section, then it will be a same at top and bottom. But since the cross section is not symmetry about any horizontal axis, so that's why the top and bottom stresses were different, and we have to consider both values in compression and tension for both the point at B, D, and C. So, and the allowable load we can apply to this is 7.01 KSI. Okay. Now, for sections 5.3, these are the assignment problems, and there are some other reading assignment as well. So please go through this concept application 5.4 and also this sample problem 5.7. We already did 5.8. So please go through this 5.7 and it will further clarify your concept. So thank you very much. This we wind up chapter 5, and uh, we will start chapter 6 from the next lecture. Thank you very much. Now, if you have any question or